Good morning. No? So in the last class, we just started the instruction set of the DSP processor. So this particular instruction set is quite different compared to your normal 8086 microprocessor. Don't get confused with that one. So the load and store instructions, we started the load instruction. So under the load instructions, we have seen the three, and let us go for the store instructions. Okay, now if you are going through the textbook, definitely you will not get the complete information. One more thing is not only this one, if you want the clear information actually about the LACL more specifically, then what you do is go to your what is that TMS 320C 5X DSP processor user guide. So LACL, right? This instruction. Let us see that one. So you will get the clear information about this particular instruction in the user guide. Okay. Yeah. So this is what we are having. So here it is indicating that we are having it is supporting the three different types of addressing modes. One is the direct addressing mode, next one is indirect addressing mode, another one is the short immediate addressing mode. Okay, now, so this particular instruction load accumulator lower byte. Load accumulator lower byte instruction is able to perform, can be operated, or it is able to perform three different types of addressing modes: direct addressing mode, indirect addressing mode, and short immediate addressing mode. So the main intention of this one is load the accumulator lower byte with the specified data. So here DMA is nothing but we are reading the information from the address specified by the DMA part, data memory address. We are reading the information from the data memory address, or we are reading the information from the address specified by the auxiliary register, or we may reading loading the short immediate value into the accumulator. Okay, if you want, you can see that information. Yeah, look at this one. The direct addressing, it is performing the direct addressing mode, and 0 to in the direct and indirect addressing mode, it is accumulator is a 32-bit number, as we know that it is a 32-bit register. So higher word is filled with the 0, and the lower word filled with the DMA. That is a data which is specified by the data memory address. Data memory address means, as I told you, that whatever the instruction, whatever the value as writing as a part of the instruction here. If I'm writing the 09, 09 is indicating the address. So the data available in that address will be loaded into the accumulator lower byte. Don't get confused with that. So don't think that whatever the information you are writing as a numerical value over here, it is specifying the data. Actually, it is not specifying the data. It is representing the address. The value available in that address should be loaded into the accumulator lower byte. Accumulator lower byte, right? So let's go back to our explanation. Continuation to the explanation. So this is the information from the from the user guide, which clearly explains each and every point. But this much is not required for you as at the student level. So that's why I prepared this document. You better go through this particular document. Okay, better go through this one. Yeah, the next one is the store instruction. SACB is nothing but store the previously we have the LACC, right? LACB instruction, which is loading the accumulator buffer value into the accumulator register. But SACB is quite opposite to that one. The accumulator value copied into the accumulator buffer. Accumulator value is copied into the accumulator buffer. And another instruction is store the accumulator with the higher byte. Store the accumulator higher byte. Okay. So Seema, let me say one important point. We have the load instructions and another one is the store instruction. Let me give you a brief explanation to realize this one. Load instruction is nothing but which loads this particular means the set of instructions which comes under the load. The set of instruction which comes under the load specifies that load the data available in the memory location. Load the data available in the memory location into the specified register. Into the specified register means the data is copied or loaded from the memory. So this block is indicating the memory. This block is indicating the memory, and the values is loaded into the specified register. So I'm assuming it is an accumulator. Okay. So this is what we have in the load instruction. But if you come to the store instruction, in case of the store instruction, it is the opposite. The data available in the accumulator is copied into the specified memory location. It is the opposite to the load instruction. It is opposite to the load instruction. Means we have the accumulator and we have the memory location. It is a memory. It is a accumulator. Okay, the data is copied from the accumulator into the memory. It is copied from the accumulator into the memory. But this one copied from the memory into the accumulator. That is the difference. Load is nothing but from the memory into the specified register. Store is nothing but from the specified register into the specified memory location. So just remember this point, then you can easily realize the concepts. Okay. So here you are having the SACH instruction, which is nothing but store the accumulator higher byte. The content of the accumulator are shifted to the left side, shifted left, whatever the shifting operation. Yeah, let me tell you one more important point regarding the shifting. We have taken the shifting operation. All those shifts are the left shift. We don't have any right shift. All those shifting operations are the left shift. We don't have any right shift. And one more thing is, we have taken the shift to 2. Shift to 2 option is indicating that it's a 0 to 7. Shift operation is 0 to 15. Shift to operation is indicating that 0 to 7 means 8 locations, 8 shifting operations you can perform. Either to the left side, 8-bit positions, 8-bit position, either you to the left side, it is always to the left side, not the right side actually. I'm sorry. So the shifting operation is always done to the left side. The shifting operation is always done to the left side, and whatever the shifting operations which we are having, all those are the optionals now. They are not the mandatory, they are the optional. Okay. So this particular instruction. So if you want to realize the SACH instruction, let us go back. One more thing is in the document I have sent this particular document to you. You better to move in the backward direction. In the backward means upward direction. We are having the 16 number now. Number 16 in your document, which is a 41 pages document. Number 16 is the first page. You are supposed to consider like that. If you go back, 15 is the second page. Okay, this is the 15th page. 15th page is the second page. 14th page is the third page, and so on. Reverse order. Okay. So we have seen this particular SACH instruction. SACH instruction. What it is performing is, it is copying the accumulator content into the specified memory location. Before copying the value, it is shifting the accumulator content by the shift number of times, which is the shift to means 0 to 7 times. So between the 0 to 7 times, how many number of bits you are, how much value you are specifying, that many number of times the accumulator content is shifted, and the result of the shift will be loaded into the specified memory location. Result of that particular shift will be loaded into the specified memory location. Okay. So which means, let us suppose I'm having the accumulator. Let me take the reverse order. I'm having the accumulator value, which is a 0006. I'm not specifying the 32-bit number, make it as a 32-bit. Okay. So for explanation point of view, I took only the 16-bit number. Actually, it should be the 32-bit number. So I would like to shift this one. I would like to perform the one shift operation. Means the content available in the accumulator is a 0006, and I would like to load this value into the memory location. Okay, now. So memory location, I am assuming that memory location is the, let me take the 0A. 0AH is my memory location. 0AH my memory location. Okay. So I'll give the explanation for this instruction. After that, we'll move with the explanation only. Okay. More explanation. It is a detailed explanation. So here we're having the instruction like this now. Actually, we have the instruction for this operation is what is that? SACH. SACH. This is what the instruction we have, and the syntax, complete syntax is SACH. If I'm specifying the address, what is the address? 0A is the memory location, comma. I would like to shift this one to the left side by 1-bit position. As I told you that this is a shift to 2. You can take any value between the, sorry, it should not be the hexadecimal number. For the hexadecimal number, it is very difficult. It should not be the hexadecimal number. It should not be the hexadecimal number. It should be the 0AH is the address, which is the hexadecimal number only. But this shift number should be the normal normal decimal number. Okay, now. So I'm specifying this one as a 01. I'm not writing the H. I'm sorry, in the previous video also, better not to consider the H. Okay. So 01 means one time I would like to shift this content to the left side. So that is what we are specifying over here. We are having the accumulator content. That accumulator content should be shifted by the shift number of times. So that is nothing but the 1-bit position. That is nothing but the 1-bit position. And after shifting, whatever the result we are having, that should be loaded into the specified memory location. That should be loaded into the specified memory location. What is the memory location over here? 0AH. But in the last video, we have seen that if you are performing the left shift operation on the 6, it becomes a what is that? The shifted value means the shifted value is a 1-bit shifted value is a ACC becomes 000C. In the last video, we have seen this one, right? So this particular 000C will be loaded into the 0AH memory location. Okay, and after shifting, this value is copied into the 0AH memory location. Okay, so this operation is nothing but what? It will load the accumulator content into the memory location, which is a 0AH, and I'm specifying the shifting operation. If I'm not specifying, only the 6 will be accumulator content is directly loaded into the specified memory location. But if I'm specifying the shift code, then that many number of bits position, it will shift to the left side, and the result of that operation will be loaded into the memory location, specified memory location. So that is what we are having the SAH. That is what we are having the SAH. Next one is the SACL. So here also SACL. Here also we are able to perform the direct addressing mode of operation as well as indirect addressing mode of operation. The operation looks like this. Previously, we have taken in the previous explanation, we have taken the complete accumulator. It is a complete accumulator. This one is a complete accumulator, but a complete accumulator means it is a 32-bit number. But here we are taking the SACL, which is a lower word. Lower word means accumulator, lower word only. Accumulator lower word only, shifted to the left side, and result of this particular shift will be copied into the specified memory location. Are we clear? So this is what we are having. Okay, but what about the higher words? Means higher words are filled with the 0. Whatever the accumulator higher word is there, which is a 32-bit number, right? The total one is a 32-bit number, but the lower word is a shifted value. Higher word is filled with the zeros. And when we are performing the left shift operation, it is saying that the lower bits are filled with the 0, which we have seen in the last video. Next one is a SAMM. SAMM is nothing but store the accumulator content into the memory mapped registers. MM is nothing but the memory map registers. MM is nothing but the memory map register. Store the accumulator content. SAMM is nothing but store the accumulator content into the memory map registers. Okay, and memory map registers means we have seen one explanation under the memory map explanation in the architecture of the DSP processor. We have seen that we have the 96 memory map registers. 96 registers are there in the CPU of the DSP processor. These 96 memory locations, 96 registers are mapped into the page 0. We have seen that one, right? Page 0. It is mapped into the page 0. Okay. So means 96 registers are there. All these registers are mapped into the page 0. All these registers are mapped into the page 0, right? Page 0. Okay. So here SAMM is nothing but the content available in the accumulator. If you want, you can see this one. The content available in the accumulator, this particular accumulator, that will be loaded into one of the 96 register available in the page 0. It will be loaded into one of the 96 registers available in the page 0. If you see this one, we are having the data memory address. Page 0 is available in the data memory. It is not in the program memory. Program memory divided into blocks format, but the data memory is divided into the page format. Okay, now. So here, actually, the data memory page should be indicated with the 16-bit number, but we are having the 8-bit number only. Why? Because when you are taking the page 0, in the last class we have seen that the data page pointer, we are having the DP now. So DP is indicating the 9 bits. So 9 bits are there, and these 9 bits are available in the DP register. But as we are performing the memory mapping operation, okay, memory mapping means accumulator content is loaded into the memory mapped area. Means registers are mapped always into the page 0. So that's why DP is always filled with the zeros. Means we are not interested in these 9 bits. We are interested in the remaining 7 bits. Sorry, 8 bits. We are interested in the remaining 9 plus 8 is a 17, right? No, it should not be 8 bits. It is a 7 bits only. 7 bits only. Okay. Now. So these 9 bits are concatenated with the 7 bits. So these 7 bits are indicating the 0 to 6 actually. It should be the 0 to 6 which is indicating the 7 bits. So these 7 bits are more than enough. 7 bits means it is a 0 to 8 bits is a 5 to a no 256, right? Totally it is a 256. Page 0 is a 256. 9 plus 8 is a 17, right? It should not be like that. It is a yeah, it is only the what is that, 128 memory locations are there in the page 0. 128 memory locations are there in the page 0. In those 128s, this DMA is indicating the one of the memory location in the page 0. So that is a SAMM. Okay, now that is a SAMM. So if you see this one, the DP is always filled with the DP is indicating the page 0, which is always filled with the zeros. Okay, now because the registers which are there in the CPU, the 96 registers which are there in the CPU, they are directly mapped into the page 0 of the data memory, not in another page. Okay, now they are available directly in the page 0. They are directly available in the page 0, and whatever the address you are specifying over here as a DMA, that address is nothing but one of the register which is mapped into the page 0. One of the register which is mapped into the page 0. Okay, so this is about your store accumulator register. Sorry, store the accumulator content due to the one of the memory mapped register. is nothing but the memory mapped register. Those memory mapped registers are available in the page 0. Those memory mapped registers are available in the page 0. So that's why we are having the this one. So it is indicating that accumulator lower byte, accumulator lower word. I'm sorry, accumulator lower word is copied into the one of the memory location available in the page 0. One of the memory location available in the page 0. The next one is the addition instructions. Okay, now addition instruction, addition and subtraction, or I can say that the arithmetic instructions. Okay, now addition, subtraction. So addition ADCB. ADCB is nothing but it is adding the accumulator content with the accumulator buffer along with the carry. So if you see this one, accumulator content is added with the accumulator buffer register along with the carry. Result of this addition will be copied into the accumulator only. Next one is the ADD. ADD space DMA comma shift means it is adding the content available in the, if you want you can see this one. This particular addition, previously ADCB is there, it is a with respect to the accumulator buffer and the accumulator register, but ADD instruction is able to perform the different types of addressing modes also. One is this is a direct addressing mode of operation. ADD DMA is a direct addressing mode of operation, and it is an indirect addressing mode of operation. It is a short immediate addressing mode. It is a long immediate addressing mode. Okay, now. So again, we are having the shifting before performing the addition of the data specified by the this particular memory. That is get shifted means the data which is specified by this particular memory location is shifted by the shift number of times, and result of that particular shift is added with the accumulator. Final result will be there in the accumulator. If you want to see this one, for this particular one, we are having the 4 types of addressing modes. Means ADD is supporting the 4 types of addressing modes. For this, the explanation is looks like this. Okay. So this is what we are having the explanation. Okay. If you see this one, for the direct as well as the indirect addressing mode, the data which is available in the accumulator is added with the data which is specified by the DMA address, and this particular data available in this particular address may or may not be shifted. If you are using the shift code, then it will take the data from this particular memory location, shift that one by the shift count value means how many number of bits it should be get shifted, that many number of times the content which is specified by this particular memory location gets shifted, and result of that this particular shifting will be added, means this result will be added with the accumulator, and final result will be stored in the accumulator. Okay, so means accumulator is added with the data specified by the memory location, that may be get shifted or may not be get shifted, that is the optional one, and result of this particular one is added with the accumulator. Final result will be stored in the accumulator. We have seen the short immediate now. So here the 8-bit number is directly added with the accumulator, and final result is there in the accumulator. Here the 16-bit number is added with the accumulator. But here we are having the optional shifting. Means if you want to get this particular 16-bit number get shifted or may not be shifted. If we are not using the shift code, then directly 16-bit number is added with the accumulator. Result will be stored in the accumulator. If we are using the shift code, then this particular 16-bit number get shifted by the shift code times, and result of this particular shifting will be added with the accumulator. Result of this particular shifting will be added with the accumulator, and final result will be stored in the accumulator itself. Final result will be stored in the accumulator itself. Okay, now. So this is about your the last instruction, which is a what is that? ADD. Okay, now. Addition operation. The next one is the ADDV. Okay, now. Sorry. Yeah. The next one is a ADDB. So previously we are having the ADCB. ADCB is nothing but accumulator, buffer register, and carry flag. But ADDB is nothing but accumulator and the buffer registers only. ADDB for accumulator and buffer register. Only these two contents are added. Result of that one will be stored in the accumulator. And we are having the ADDC. So ADDC space DMA means again we are having the memory location. The value which is specified by this particular memory location. So means here we are writing the memory location. Whatever the value is there in that particular memory location, that will be added with the accumulator along with the carry. Okay. So accumulator content is added with the memory location content along with the carry, and result will be stored in the accumulator. Parenthesis indicating that it is a representing the value. DMA indicating that means the value available in this particular memory location is replaced with this particular term, and carry flag bit position replaced with this particular term, and finally these three get added. Result is there in the accumulator. So the next case is the ADDSB. ADDSB is nothing but here we are directly adding the content available in one of the memory location with the accumulator. If you want, you can see this one. Look at this. So the content available in the the content which is specified this particular memory location will get added with the accumulator, and final result will be stored in the accumulator itself. Next instruction is the ADDT. Okay, now ADDT along with the DMA, which means DMA is nothing but the data memory address. So in this case, if you want, you can see this one. So I think what was the previous page number? I forgot to see the page number. Wait a minute, it is the third page and it is a fourth page. Yeah. So this particular instruction, what it will do means, this one is depends on the sign extension mode bit. So actually we have seen the sign extension mode bit in the status register 1 concept. Okay, now during the explanation of the status register 1, I told you what is the importance of the sign extension mode bit. Okay, sign extension mode bit, but forget about that one. We are having the content of the accumulator. Content of the accumulator is added with the memory data specified by the memory location, and this data may shifted by the temporary register 1. We have seen the temporary register 1 in the product multiplication case during the explanation of the CALU block available in the microprocessor, that is the DSP processor. I told you that the DSP processor is able to perform the 16-bit by 16-bit multiplication. Okay, in that multiplication we are having the barrel shifter also. Result of that particular multiplication may be get shifted and loaded into the product register. So that particular barrel shifting operation is done based on the content of the temporary register 1. Temporary register 0 is storing the multiplicand value, but temporary register 1 is indicating the shift value. How many number of bits the content should be get shifted. So here it is indicating that DMA content, that is a data which is specified by this particular address, that is a DMA address. Don't get confused. Again, I am saying that DMA is nothing but it is not the direct memory access, it is a data memory address. This particular address is indicating the memory value. So that value gets shifted by this particular number of bit positions specified by the temporary register 1, and the result of this particular shifting will be added with the accumulator, and final result will be stored in the accumulator. And we are concentrating on the sign extension mode bit in order to avoid the confusion regarding this particular instruction set. I'm not explaining much about the sign extension mode. Better to leave the sign extension mode bit. So the main intention of the sign extension mode bit to carry forward the sign of the number. So when you are performing the signed arithmetic operations, which will, at that time this particular sign extension mode bit plays a major role. Okay, now. So when you are performing the signed arithmetic operations, at that time sign extension mode bit plays a major role. But if you are performing the unsigned arithmetic operations, then we are no need to consider about the means we are least bothered with the sign extension mode bit. Okay. Next case is the ADRK. ADRK is nothing but the see the immediate value write justified. Okay, now write justified is added to the current auxiliary register and the result is stored in the AR. Current auxiliary register. So what is the current auxiliary register? Means which AR register is presently used. How many AR registers we are having? AR0 to AR7 are there, right? AR0 to AR7, AR0, AR1, AR2 and so on to the AR7. So which register, which one means which bit combination is indicating which auxiliary register is currently available, means currently in use. Which auxiliary register is currently used, that is indicated by the ARP bit position. I don't know how many of you really remember this one. We are having the ARP, right? Auxiliary register pointer. So this particular auxiliary register pointer is indicating which auxiliary register is currently in use. So that particular auxiliary register content is added with the 8-bit positive constant, that is the 8-bit number, and final result will be there stored back into the same auxiliary register. So let us suppose present auxiliary register. I am assuming that AR3 register is in available presently, and I am assuming that the 8-bit positive number is there now. I am assuming that this positive number is a 03H, and final result will be stored in the AR3 only. So if at all I am assuming the AR3 value as the content available in the AR3 register is a 06H plus this one is added with the wait a minute, I'll take one more. Yeah, 06 is available in the AR3 register, 06H plus 03H, and final result will be there in the AR3, which is nothing but the 09H, and which is there in the AR3. So this is what we are having regarding this particular instruction. Okay, so this is about the addition instructions, and next case is a subtraction operation. So SBB is nothing but accumulator buffer content is subtracted from the accumulator register. Result will be stored back into the accumulator itself. And one more SBB instruction is there, but here we are having the 3 BBs, means along with the borrow. Subtract the accumulator buffer register from the accumulator along with the borrow. Means carry flag is called as a borrow flag, which will get inverted. The inverted carry flag, which is called as a borrow flag in the subtraction operation, subtracted from the accumulator along with the buffer register. So final result will be stored in the accumulator itself. Let us go to the another instruction, which is the SBRK. Just like ADRK, we have the SBRK. So 8-bit positive number subtracted from the current auxiliary register content, and the result of this operation will be stored back into the current auxiliary register. The next one is the SUBB instruction. So SUBB along with the DMA. Is nothing but the DMA content, that is a memory. DMA is specifying the memory location. The value available in this particular memory is subtracted from the accumulator along with the inverted borrow or inverted carry flag. Result will be stored into the accumulator itself. Next one is the SUBS. So which is nothing but subtracting the data available in this particular memory location from the accumulator, and stores the final result in the accumulator itself. Back into the accumulator itself. The next one is the move instructions. BLDD stands block move data, means a block move register. The block move instruction, it is a block move instruction from the data to data, means from the data memory to data memory. So this one is the BLDD is nothing but block move instruction, which copies the data from the one of the data memory location into another data memory location. Means the data is transferred within the data memory only, from one page to another page, or from one location to another location in the within the same page. Okay, so within the same page. DD is nothing but the data to data. DP is nothing but the data to program. Okay, remember that point. DD is nothing but the data to data. DD is nothing but data to data. DP is nothing but data to program memory. So what I mean to say that, let us suppose I'm having the what is that, two pages. We know that the data memory is divided into the page format. Okay, so it is, I'm assuming that it is a data memory. Now I'm assuming it has a page 0, right? Page 0, and I'm assuming that it is a page 1. Is a page 1. So here the source is the one of the data memory location. Destination is also one of the memory location. And one more point is, remember in the advanced microprocessors, in the DSP process, in the 8086 microprocessor, we have the syntax for the what is that, move instruction, right? Move destination comma source. Okay, let me take the caps. We have the instruction move space destination comma move space destination comma source. Okay, so in the 8086 microprocessor case, left operand is indicating the right operand is indicating the source, left operand is indicating the destination. But in the advanced microprocessors like 80286, 386, 486, Pentium Pro, Pentium MMX, and other advanced microprocessor, in all those microprocessors, the move instruction is quite different. It is a source comma destination. It is a source comma destination, right? So means right operand is indicating the destination, left operand is indicating the source. Here in the DSP processor also, right operand is the destination, left operand is the source. Okay, BLDD is nothing but copy the data or block move operation. I can say that it is a block move operation. Copy the block of data or copy the data from the data memory location to another data memory location. That may be within the same page, or that may be within the data may be from one memory location to another memory location within the same page, from one memory location to another memory location in the another page. Like this, we have the 512 pages, but I am taking only the 2 pages for the explanation point of view. Okay, now. So here, whatever the addresses you are taking, that is the source and the destination, those are indicated by. So if you see this one, the content of the data memory address pointed at source are copied to the data memory address pointed at by the destination. The source and destinations spaces can be pointed by the long immediate value, the content of the block move address register, or the DMA, right? So means these source and destination may be this particular source. Actually, the source is always the immediate value. The source is always the immediate value. The destination won't be the immediate value. Remember that point. Source is always the immediate value, but the source is always the immediate value. It is the immediate value, as well as it may be the block move address register, as well as it may be the memory location. But the destination may be BMAR, that is the block move address register, or the DMA, but it should not be the immediate value. Remember that one. Okay. In case of the source may be any immediate value, or it may be the BMAR, block move address register, or it may be the DMA, which is a memory location. But if you come to the destination may be the BMAR or DMA, but it should not be the immediate value, because in the destination position we are not having the immediate value. Remember that point. Okay, now because in the in the microprocessor case also, in the 8086 microprocessor also, you would have seen. Wait a minute. In the 8086 microprocessor also, you would have seen move AL comma 02H, which means 02 is copied into the AL, but you would have not seen the instruction like this: move space 02H comma AL. Okay, now this instruction is a false instruction, because destination should not be the constant. It may be the memory location or it may be the register, but it should not be the constant. So that's why here in the source and destination position, source may be the constant value, that is the immediate value, or it may be the BMAR, or it may be the DMA. But the destination is always the BMAR or the DMA, but it should not be the immediate value. It should not be the immediate value. Okay. So this is from data to data, data memory location to data memory location. But if you come to the bottom one, the bottom one BLDP, again it is a block mode register operation only. Okay. Okay. So DP is nothing but data to program. It is a data to program. If you see this one, the content of the data memory address are copied to the program memory address at that is a block move address register. Means this particular program memory is specified by the BMAR. The source and destination blocks do not have to be entirely on chip. Okay, no. So it may be the on chip or the off chip. It should not be always the on chip. Okay, no. It should not be always the on chip. Okay, next one is a BLPD. Previously, BLDD is a data to data, BLDP is a data to program memory, and BLPD is nothing but program to data memory. Program to data memory. Program to data memory, and the source and destinations are differ one. You can go through this point. The next one is a TBLR. The content TBLR space DMA, which says that the content of the program address are transferred to the data memory address. The program memory address is specified by the contents of the accumulator lower byte, and the DMA is specified by the instruction. Okay, now a read from program memory is followed by write to the data, complete the instruction. Okay, now read from the data program memory is followed by the write to the data memory. Means we are reading the information from the program memory, and that information is copied back into the data memory. Okay, now so the information which is specified by the PMA, means here we are having the three parts now. The TBLR is performed in the three parts. One is the program memory address to the, let me take the small letters, program memory address to ACC lower byte, program memory address to ACC lower byte to, what is that? DMA. Means first data is copied from the program memory into the accumulator. The data which is available in the accumulator again stored into the data memory. Okay, so that is about the TBLR, right? So it is a 8-bit, that is a 16-bit format. Now, if you come to the DMA, that is a TBLW. Wait a minute. TBLW. So in this case, the content of the DMA are transferred to the program memory. The DMA is specified by the instruction. Yeah. Previously, the content of the program memory address are transferred to the DMA, but in this case, the contents of the data memory are transferred to the program. It is in the reverse order. Okay, now previously, program memory to the accumulator lower byte to the data memory, but in this case, data memory to the program memory via the accumulator, right? So here, via the accumulator means we have a small difference in this explanation. Okay, what is that is, I told you the accumulator, via the accumulator, na? Accumulator lower byte is specifying the program memory address now. Okay, now so in the previous one I took the PMA followed by ACCL followed by what is that, DMA, right? So here in this case, in this particular instruction, the data is copied from the program memory into the data memory. But have you mentioned the PMA value, that is the program memory address, as a part of this instruction? We have not, right? Have you mentioned any program memory address as a part of the instruction? We don't have it, but the DMA is there. So here the PAM, that is the program address memory. Sorry, it is not the PMA. It is a PMA. I'm sorry, it's a PMA. I got confused. PMA. Program memory address is indicated by the lower order accumulator. Lower order accumulator word is indicating the program memory address. From that particular means the content of the accumulator lower word is taken as the address. That address is a part of the program memory, and that value is copied back into the DMA. What I mean to say that we have the two memory locations. So I'm assuming that it is a actually it is a PM, program memory address, not the PAM. It is a PMA, program memory address, and this one is a data memory address, DMA, right? So the data memory address is mentioned as a part of the instruction itself, but the program memory address is not mentioned. So this particular program memory address is indicated by the accumulator. It is indicated by the accumulator lower byte. So whatever the content which is there in the accumulator lower byte, that is specifying the one of the memory location in the program memory, and from there means this particular content is specifying the memory location in the program memory, and whatever the value is there in that particular program memory, that is copied into the data memory. That is copied into the data memory, which is specified as a part of the instruction itself. Okay, so actually it is not from the what is that program memory address means. I told you that the data is copied from the program memory address into the accumulator lower byte, accumulator lower byte to the data memory address, but it is not like that. Actually the accumulator lower byte content is used as a address within the program memory location, and from there it will read the value and copy into the data memory. What I mean to say that accumulator lower byte word is indicating the address within the program memory. From that address, whatever the data is there, that is copied into the data memory. That is copied into the data memory. That is about the TBLR. But if you come to the TBLW, in this case, the content of the data memory address means it is a data to program. But in this case, again, the accumulator lower byte is indicating the PMA value. Again, the accumulator lower byte is indicating the program memory address. Accumulator lower byte is indicating the program memory address. Okay, so don't get confused. So the PMA to accumulator to DMA was right, but accumulator lower byte is indicating the address within the program memory location. Okay, now within the program memory address within the program memory. The next one is a yeah, we done with the addition operations, and we'll go to the what is that? Which one we are in the 10th page, right? The multiplication instructions. We'll go to the multiplication, shifting operation, and all those things, right? Yeah, we'll go to the multiplication. Multiplication. So MPY is nothing but multiplication. So I told you that we are having the 16-bit by 16-bit multiplication. So one of the 16-bit register, 16-bit value specified by the temporary register 0. We have seen this one in the CALU block, Central Arithmetic and Logic Unit block. Central Arithmetic and Logic Unit block. So what I mean to say that we are having the 16-bit by 16-bit multiplication. 16-bit by 16-bit multiplication. So the multiplicand is there in the temporary register 0. And the multiplier, this particular multiplier may be the immediate value, or it may be the register content, or it may be the memory location. So in this case, we are indicating the memory location. So in the MPY case, the memory location content is multiplied with the temporary register 0. Result of this one will be copied into the product register. The result of this multiplication will be copied into the product register. Okay. So the next one is the MPYA. In this case, first of all, accumulator content is added with the shifted product register, and result will be stored in the accumulator. After that, the temporary register 0 is multiplied with the DMA. Result of this one is there in the product register. If you want more information about this one, MPYA, let us go over here in the MPYA, right? Yeah, if you see this one. So first of all, the shifted product register is added with the accumulator, and result of this addition will be stored in the accumulator. After that, the temporary register 0 content is multiplied with the DMA, that is a data memory address, the content which is specified by this particular memory location, and result of this one will be stored in the product register. Result of this one will be stored in the product register. Okay, now, so that is about the MPYA. Next one is the MPYS. So previously it is a YA means addition. YA means addition, multiplication only. But before that, the product register is added with the accumulator. And if you take the MPYS, it is a subtraction. Means the shifted product register, that is the product register content, is subtracted from the accumulator. Result of that one is stored back into the accumulator. After that, it is performing the multiplication between the temporary register 0 and the DMA, and result will be stored in the product register. And we are having the MPYU. MPYU means multiplication between the two unsigned numbers. Multiplication between the two unsigned numbers. We are having the two unsigned numbers. The next case is a shifting operations. Okay, shift logical instruction. Okay, so shift and the logical instructions. So we are having the first logical operations like AND operation and OR operation. After that, we will go to the shifting operation. Okay. So if you see this one, AND B is nothing but it is a logical AND operation between the two operands, which is a accumulator and accumulator buffer register. Accumulator and accumulator buffer register. After what we do, after the logical AND operation between these two content, final result will be there in the accumulator. Final result will be there in the accumulator. Okay, now. But here I am not defining the AND operation. During the explanation of the instruction set of 8086 microprocessor, I have defined the what is the AND operation, what is the OR operation, what is the exclusive OR operation, all those things. Okay, so it's a AND operation between the two operands, which are the accumulator and accumulator buffer register. And the next one is a AND along with the DMA. Okay, here we are performing the direct addressing mode of operation, indirect addressing mode of operation, and the long immediate addressing mode of operation. Okay, so if you take the direct and indirect addressing mode of operation, first of all, the here the AND operation is between the DMA content and the lower word of the accumulator. It is the AND operation between the DMA content and the lower word of the accumulator. Result of that one will be stored in the accumulator lower word, and the accumulator higher word filled with the zeros. Accumulator higher word filled with the zeros. Accumulator higher word filled with the zeros. And if you come to the immediate case, look at this one. Accumulator lower word is logically ANDed with the immediate value. ANDed with the immediate value. And this particular AND operation, before the AND operation, if you want, you can perform the shifting operation on the long immediate value, which is a 16-bit number. After shifting, whatever the result you are getting, that will be ANDed with the accumulator lower word, and final result will be stored in the accumulator. Again, in the higher order word of the accumulator is filled with the 0. Again, the higher order word of the accumulator filled with the 0. Okay. So this is about the AND operation, and we have the OR operation. OR operation again similar to the AND. Okay. So OR between the accumulator lower word and the lower accumulator. OR operation between the accumulator lower word and the DMA. Final result is there in the accumulator lower word. Previously, accumulator higher word used to fill with the 0, but in the OR operation, accumulator lower word, higher word is same. We don't have any modification. So go back to the what is that? ORB. ORB is nothing but the again accumulator OR operation between the accumulator and accumulator buffer register, and finally result is there in the accumulator buffer. We are having the exclusive OR operation XOR. XOR is nothing but I'm not interested to define again. So if you want the definitions for the AND gate is nothing but if any one of the input is 0, output is 0, or if all the inputs are 1s, then the output of the AND gate is 1. OR gate is nothing but if any one of the input is 1, output is 1. Or if all the inputs are 0s, output is 0. And exclusive OR operation is nothing but if odd number of 1s are there at the input of the XOR gate, then the output is 1. If odd number of 1s are there at the input of the XOR gate, then the output is 1, otherwise the output is 0. Which means if even number of 1s are there or zeros are there, then the output is 0 in the XOR gate. Okay, now. So XORB is nothing but exclusive OR operation between the accumulator and accumulator buffer register. And after that we are having the ROL, rotate operation. we are having the rotate operation. The content of the accumulator are rotate left by 1 bit position. If you are not specifying any count value, it is obviously 1 bit position. The value of the C bit is shifted into the LSB. So what I mean to say that, so here, if you want the diagrammatic explanation, we have the diagrammatic. Wait a minute. Let me take the caret flag. ROL is nothing but the rotate left. So I'm assuming this one is a. Let me take one more in the diagrammatic manner. I'm giving this one. I didn't prepare the slides for this one. That's why there's a problem. The data will be in this direction. Again, the data will be in this direction. And the data will come out from the caret flag. Sorry. Caret. So look at this one. We have the caret flag. CY. Let me take the caps. CY. And this is the most significant bit, which is the 31. ACC 31 bit and ACC 31 bit, and it is a 0th bit. That is the LSB, because the accumulator is a 32-bit number. So this 31 bit is copied into the carry flag, and the carry flag value is fall back into the lower bit LSB value position. MSB of the accumulator is copied into the carry flag, and the carry flag bit position is copied into the LSB. Okay, so that is what they are indicating over here. If you see this one, carry is copied into the accumulator lower bit, that is a 0, and the accumulator higher bit MSB is copied into the accumulator. And we have the shifting, means 30th bit is copied, shifted into the 31 bit, 29th bit is shifted into the 30 bit, and so on. And this particular 0th bit is copied into the first bit. So that's why we are having the accumulator 30 to 0 into the 31 to 1 bit position. So this is what the rotate operation. Okay. So now let's go to the rotate right. So in the rotate right case, arrow marks are reversed. Same diagram, but the arrow marks are reversed. Okay. So carry is copied into the MSB bit position, and LSB is copied into the what is that, carry bit position. Okay. Now, so let me take the red color. Let me override this one. So this one is out and loaded into the carry flag. Carry flag is copied into the MSB of the accumulator. From there into the, means the internally shifting operation is done. The rotate operation is done. So this is what the diagram. Quite opposite to the left operation. Quite opposite to the left operation. So if you see this one, look at this. So let us compare. If you want, you can compare this one. I think one bit is not indicated over here. So if you see this one, carry to 0 now. Over here we are having the carry to 0. It is a left operation, but in case of the right operation, carry to 31. It is a right shift. And LSB is copied into the carry flag. LSB is copied into the carry flag. If we go back to the next page, then 31 to 1 is into the 30 to 0. It is a right shift operation. Okay, it is a right shift operation. Next one is a negation. Next one is a negation. So NEG is nothing but the negation. It is the replacing the content of the accumulator with the 2's complement form. It is replacing the content of the accumulator with the 2's complement form. So I think in the last class, I would have raised one question that instead of representing the negative numbers in the 1's complement form, they are using the 2's complement. How many of you realized that one? I don't know. Let me know that one. Why they are using the 2's complement to represent the negative numbers, and in place of the 1's complement. Instead of representing the negative numbers in the 1's complement, they are representing the 2's complement. Why? It is a question. If you are having the answer, let me know in the group. Okay. So negation, it is performing the 2's complement operation. The content of the accumulator are replaced with the arithmetic 2's complement. Okay, now means this one. 2's complement is performed. 2's complement is performed on the accumulator content. Result will be stored back into the accumulator. If the after 2's complement, if the accumulator content is not 0, then the carry flag is filled with a 0. After 2's complement, if the accumulator content is 0, then the carry flag is a 1. Carry flag is set to 1. Okay. Next one is a complement operation. Complement is nothing but it is performing the ones complement operation. Negation is performing the twos complement operation, and CMPL is performing the ones complement operation. Okay. So we'll continue with the norm instruction in the next class. It is a very important instruction as per your semester exam. Okay, norm instruction, and rest of instructions we'll see in the next class. We'll see in the next class. So I'm stopping the this class. If you are having any queries regarding the instruction set, let me know in the group. And one more thing is, it is not means the instruction set of the DSP is quite different compared to the other microprocessor now. Okay, now you are supposed to put a little focus on this particular instruction set in the DSP processor. Okay, if you know the instruction set and the addressing modes of the DSP, then you can easily get the 20 marks as per your semester exams. Okay, now 20 marks. Okay, now semester exams, addressing modes and the instruction set from the fourth unit. Okay, we'll continue in the next class with instruction set.